So I think this is probably going to be quite a high level talk. I don't really have any specific case studies that I'm going to talk about. So it's kind of coming at it from the side of general strategy with automation, data management, that kind of thing. In high throughput experimentation, which is what my background is in, then we're dealing with a lot of data, but typically people who are working with high throughput don't have particularly a data science expertise, don't have any training in that sort of thing. And quite often, even with really big companies, you will see just a dump of data happening somewhere, which is something that we're really trying to avoid. So I'll start off by telling you a little bit about Syngenta, just quickly. So this is us in the UK and Ireland. We're a big global company. I should really add in a slide at some point about Syngenta in the world rather than just the UK and Ireland, but maybe it's useful from a recruitment point of view, I don't know. But anyway, this is us. We've got a bunch of different sites. I can get my laser pointer showing. On here, not too far from London, at Dollots Hill, which is our main R&D site in the UK. So we're largely focused on discovery chemistry, and that will typically be for herbicides. So that's Syngenta all around the UK, but in general, yep, Syngenta is a massive company actually with two core businesses, both crop protection, which is where I'm based, so that's mainly for me, that's herbicides, but also fungicides, insecticides. And then there are other things like seed care, which is kind of cool. So you can plant a seed that's already pre-treated with perhaps a chemical treatment that will make it grow better or outcompete weeds better or something like that. There's also the seed business, working on all manner of different things, and Syngenta flowers, which I think is really cool because it's a business that exists purely to make pretty things out of science. I think, yeah, I'm a big fan of Syngenta flowers. I don't even have a garden, but if I did, I'd just want to fill it with cool Syngenta flowers just because I get the chance to know more about them. Yeah, this is us. We do a bunch of different things on site. So I'm working in the automation lab in chemistry reaction optimization, but we also have biologists. There's a lot of formulation that's done. That's definitely a big deal for agrochem because we literally go out and spread our formulations in the environment deliberately. So also, I don't know if we say it explicitly on here, but there's a lot of toxicology and environmental studies that absolutely must be done and are completely critical and getting more and more important these days, thankfully. So yeah, so that's our the biggest research glasshouse in Europe, I believe, which is quite cool from a high throughput perspective. Then there are little plastic well plates, the same as you might use in a lab for analysis. And those each contain a little seedling in each well of the 96 well plate. So that kind of thing is very cool. Anyway, let me move on to some specific chemistry. So probably there are a lot of people here who have seen cycles like this, DSTA cycle. Most people call this a DMTA cycle, but we like to be different for no obvious reason. So it's a design, synthesize, test, analyze cycle, not a design, make, test, analyze cycle. It's the same thing, obviously. But yes, the general specific aim of discovery chemistry. So in a high throughput context, we're really focusing on this S or M part of the cycle, in which we have our own cycle, which we're calling DEA. So that's design, execute, analyze. Yeah, this slide looks like it's discovery focused. Actually, it's kind of the same deal in process chemistry or any stage of chemistry, even things like formulation, crystallization, that kind of thing, anywhere where you might use high throughput chemistry, which is pretty much anywhere chemistry happens. So yeah, not limited to discovery at all, but basically we're trying iteratively to make something better, whether it's a single reaction, a process, a crystallization, anything like that. So we'll figure out what our aims are, test them out in reality in the lab usually, analyze the results, feed them back in, get a better either mental model of what's going on or perhaps a computational model of what's going on. So really the point of the DEA cycle is that what we're doing in high throughput experimentation, or a lot of the time with automation, even if it's not high throughput, I do a lot more medium throughput these days, then we're generating data. So we're not generating compounds, which is a lot of what discovery chemistry is focused on. Most of the time, when I've finished running a 96-well plate, I will throw it all away at the end, which is quite nice. Don't have to purify or anything. I never like running columns anyway. So yeah, what I've made there is data for the company. I've not particularly, most of the time, contributed to registering compounds or making compounds. It can be done though. So yeah, I guess this is the ultimate goal of the DSTA cycle. We're trying to make things better. We're trying to make making things better as well, if that makes any sense. Yeah, we are really working on just, iteratively improving that part of the synthesis. So our data model, this slide looks complicated. It's not that bad, and I guess probably a lot of us are familiar with this sort of thing anyway, but this is how it works at Syngenta, and also kind of the ultimate goal, aim of how we want it to work. So it's not that it's not fully implemented, it's that we're continually moving towards making this happen even better, really. So we have reagent catalogs going in. I kind of wish I had more time to talk about the reagent catalogs, because from a data point of view, that's been quite a learning opportunity for me as someone who is not really a data scientist, purely a chemist, and I've worked with getting those reagent catalogs together, because publicly available catalogs, we've found we definitely have to curate them to make them work for what we want. That will be, of course, even more true if we want to generate descriptors and that kind of thing, that we can actually use in maybe generating our models for reaction optimization. But yeah, I've learned a lot about scraping things from the web and how that can be challenging when it comes to chemistry reagents. Actually, what I did a month or two ago is I went through the entire, or an entire part of the reagent database, which was, I don't remember how long, tens of thousands of compounds. And I went through it, well, I should say semi-manually. I had some scripts to help me. And it was amazing just to see the quality of data. And I shouldn't complain, the quality of data is really very high with public databases. It's just that when the quality is not where you'd want it to be, it takes quite a lot of time to fix that, because you can't really automate when something's gone wrong and a computer can't find it. A computer's told you that this is the right thing. Anyway, reagent catalogs, we have kind of going into our models, we're then scoring these reagents and enumerating them, because what we're doing is putting together a parameter space of chemicals. So I guess then that feeds into the optimization design for the particular experiment that, for example, I'm trying to run today. I need to design what I want to physically put into my 96-well plate. And that also feeds back into other models like retrosynthesis support later. When we figure out the results, I don't want them to be just thrown away after my experiment is done and after my project is done and that part of it is complete. I want it to be able to be used 5 years from now by someone in another country who's never met me, in other contexts like retrosynthesis. We shouldn't be throwing these data away at all. But yes, I will run my optimization with the help of some automation, because it's very slow to dose a 96-well plate yourself. And then that will feed back into the data lake and perhaps be able to tell me what to do next time if I'm running yet another iteration of a plate based on this experiment, or if someone else in 5 years' time is doing exactly the same thing. So the whole point of discovery chemistry is just to move fast and weed out failures as quickly as possible. It's the same in process chemistry, though. The whole point is then to do things excellently and get the best results you possibly can. But this is kind of what it looks like for me. So once I've generated my optimization design, then I use software automation and hardware automation to screen reaction conditions. This is a very young lab that I'm working in. So in terms of hardware automation, we're still building that up, and well, also with software automation, but that's a bit faster to build up if you're willing to make your own prototypes, which is what I do with Python. So I'm not an expert in that either, but I can come up with a prototype and then we can get it working. And I quite like that model where I can then pass it on to someone who actually knows what they're doing, who's a real life computer programmer, and they can make a brilliant tool that works for everybody and is robust and is maintained by someone who knows what they're doing, but also has all the features that I've put in that work really well for me. So yes, I use solid dosing robotics, liquid dosing robotics, things in 96-well plates. And then I guess one of the kind of important things about this lab is that we generate standardized data. We try to generate standardized data. It can be difficult because we're looking for so many different things. But those data are always, well, maybe not always when they can be, fully quantified with internal standards and that kind of thing, so that the computational models that we're generating for future use work well and understand in context what they're talking about. If we can't quantify something, then semi-quantified is fine. There's no point wasting hours and hours of a chemist's time trying to get internal standards and trying to get product standards if you're making 12 different things, none of which are extremely high on the list of things you care about. So there is a little bit of a trade-off there for how quantified your data are. But yeah, as I kind of alluded to, we're doing this for a variety of reasons. It's not all about yield. There's also, even at the discovery stage, there's also a lot of pressure on improving sustainability. Same with cost of goods. These sound like things that might just be useful for process, but early on we start to think about these things. In agro, then our customers, farmers, have very, very tight profit margins. So eventually, then pretty much when we get to manufacturing scale, if you have a ligand for palladium, it's going to be triphenylphosphine or nothing almost. So yeah, there's a lot of pressure going on there. And sustainability, working in agrochemistry, you might expect that to be something that's incredibly important, and it certainly is. So that's the kind of things we're looking for. I know I'm kind of preaching to the choir with this a little bit, but I really do like this paper from some GSK authors. It was in Nature Catalysis. It's a couple of pages longer perspective. They did this screen that really helps to me show why one factor at a time is not good. And I'll show you my version of an alternative model and why this works for us. Basically, these authors, I haven't even shown the reaction because what's important is what they're doing here. But it was a cross coupling. They have tried one base and one solvent. And with those, they've run 16 different ligands. So all the same conditions. The only thing they're changing is the ligand here. And they found a couple of good ones. They all seem to be phosphines that have worked out really well here. But the best of these is clearly xanthos, which has a 20 percentage point lead on BCE phos, the second best. So it looks like xanthos is definitely the best ligand here. The authors then vary Yeah, the authors then vary the base and the solvent, keeping xanthos now as a constant. And they still find that disopropylethylamine and acetonitrile are giving the best results. So with those 21 combinations that have been run, then, well, it looks like xanthos is the best ligand, disopropylethylamine is the best base, acetonitrile is the best solvent. And then the authors say this: classical screening, or one factor at a time, gives a local maximum, not a fully optimized system. This is even more important for cross couplings because there are so many off-cycle processes, weird equilibria. The mechanism can change when you change a discrete variable like the reactant that you're putting in, which tends to be the kind of optimization that I would be doing. So when they then ran a full factorial design, every combination of all the levels of all the variables that they were looking at before, then here is the result we saw earlier, 81% with xanthos, but actually there are 8 better sets of results. And the best set of results is DCPE, toluene, and potassium carbonates. So, you know, something very different is going on that has shown that one factor at a time optimization is not the way to go here. All of our guesses for ligand base and solvent were not good. So I do tend to run these full factorial designs. I know I could be running DOE and, you know, fractional factorials. Actually, in practice, it is quite often faster to run full factorial. So, you know, here I've my variables. I want to run these 12 ligands. This is a real experiment that I did a couple of years ago at Eli Lilly. And, you know, straight away, that's my design. It's done, it's sorted. I don't need any statistical manipulation at the end. And it's just very easy to do this and give it to the automation to run. So I have a Python script that as soon as I pick my 12 ligands, in this case, 2 solvents and 4 bases, I tell that to the script, and I've written the script such that it makes everything, you know, it designs everything for me. It tells me everything to do. I trust it pretty much. So it's a lot easier. Yeah, you could consider it a waste of material, but the fact is, I tend to be running these on 5 milligram scale. I'd say would be quite an average. I have gone down to 2.5 milligram scale. That's really very small. I don't tend to go that low. It's normally more like 5, but that's pretty small. So error bars are definitely high. And I think having that bit of redundancy in the results is actually really quite useful, especially considering that I tend to be using solid dispensing equipment, which is absolutely wonderful, and does tend to have a high degree of accuracy. But of course, it's not as high a degree of accuracy as if you're running something on 100 meg scale in a flask. So, you know, I think that having these full factorial designs is a pretty good way to go. It's very easy to understand what's going on. And let's look at the results here. So the colors here just refer to different components of the reaction mixture as analyzed by LCMS. So this isn't quantified. This is LCMS areas that we're looking at, just such that I can generate a pie chart that's easy to look at. I also look at the quantified results. But this is where I always head when I've run a reaction. First thing I look at is the pie chart, because that shows me everything straight away, and I can physically see the trends. So here green is good. That's my desired product. I have blue reds, those are the starting materials, and then 2 side products in different shades of blue. I do try to avoid red and green combinations now. This is old data, and I shouldn't have been using that. It's not great from a color blindness perspective. But this is what it tends to look like. So, I should also say that the size is important. So a big pie chart like this, a lot of green, is nice. It shows you that all the reaction mixture is accounted for pretty much. Whereas something very small, a small pie chart indicates that it's probably a messy reaction mixture, or at least there's a lot of material that we don't know what it is. So if it's something that isn't part of the green or red or blues, then that is accounted for by the small size of the pie chart. So there's something else in the trace. In this case, I would probably go back and look at that. If it's messy, I probably wouldn't care. If there's one peak that's contributing to all that, I might look it up and check out what's going on there, see if I can get a bit of understanding as to why this reaction's being so selective in a way I didn't want it to be. But I can see straight away, you know, immediately, this is why I love this pie chart visualization. Looks like amphos is quite good. Looks like xphos has done decently. Rufos seems to be okay. It's a little bit smaller of a pie chart there. Sodium butoxide definitely seems like the way to go, and so does toluene for that matter. But yeah, immediately, even if you're not used to this, just with a very quick explanation, hopefully like I just gave, then you can see already which results are looking great and which you might want to look a bit further into if you want to do further optimization on this. So yeah, we can kind of pick out some interesting trends here, and I could probably go into more detail on more interesting trends really, but that's the kind of thing that I like to see from my results so that I can really understand those data. So once I've done this, I won't show any examples, but in discovery chemistry, we like to see heat maps. I personally really hate heat maps actually, because they only show you one thing at once. So we might have a heat map for yield if yield is really important, which obviously it tends to be. But another useful visualization for me that I'll always do pretty much is to look at just different charts of how each of these ligands is affecting what's going on, to try and tease out combinations of variables, that sort of thing. And of course, to look at the quantified yield results, if I have them, and how those are affected by everything else. I can also use those kind of diagrams to pick up if something's gone wrong, which it might have done. If there's a very low total area across the LCMS, then perhaps it hasn't injected properly, or maybe something's got stuck, or maybe the LC is broken down or something like that. And honestly, in a big table of data, that's actually a little bit harder to see. So yeah, from a data point of view, then yeah, this is human interpretable. These pie charts are not really machine readable, are they? So we need both. We need human readable in the short term. This experiment, these results, I want to look at them and see that amphos and xphos are nice ligands here. Long term, we want something machine readable. So yeah, we need to feed these data back into a chemoinformatics cycle that's hopefully computer understandable. Yeah, so I guess this is pretty much how it goes. We consider software and data management from the start. That's kind of a big part of what I end up doing. So yeah, I guess in bench chemistry, you would consider, you know, if you're doing a new reaction for the first time, you do a literature search, you'd go through Reactlist or SciFinder, something like that, filter your results from your chemical knowledge and your intuition, and maybe things like what equipment you have. If you know, see some mechanochemistry and you don't have a ball mill around, then perhaps you don't want to do that. And then, yeah, I guess you'd run and analyze your experiments. In HTE, it's almost the same, but you kind of need a very different mindset. So you might start off with running that same literature search. I think there's quite often an over-reliance on the literature, so I really urge anybody who is working with high-throughput chemistry to, well, anyone who's working with people who are doing high-throughput chemistry to, you know, use that expertise that they're generating. There's a lot of stuff that is not in the literature that comes out from a high throughput screen, and ligands that a high throughput person knows are probably going to work pretty well for an experiment. And you just won't see them in the literature because no one's ever, you know, had the time to go out and publish on that kind of thing. So yeah, over reliance on the literature really worries me. Sometimes there's a lot of stuff that I can't say this enough. You really need to go out there and try, rather than focus too much on what people have already done, which tends to be the same thing, or standard conditions that have been always used in the project. And actually, you know, and anyone who was a cross-coupling expert would look at it and say, why are you using John Foss for that? That's just not what I'd ever have picked. Anyway, let's move on. So yeah, the main difference of high throughput is you're then searching to array a set of literature conditions and get, in my case, all the different permutations together, or at least perhaps come up with a parameter space of all the different permutations to then do a DOE experiment, which you will then run and analyze just like the bench chemist would. The arraying can be quite technical and interesting. So you may well want to use computational help and descriptors to ensure that you're sampling as much of the chemical space as you can. If it's something very unknown, you know, if you have nowhere to start from, or very little idea of where to start from, that could be a really cool idea and would at least help you to map out all the different conditions that you're planning to run. Either way, most of the time, I probably wouldn't be doing that because it takes time, and I think with enough high throughput experience, you tend to have a good amount of intuition, at least in the case of palladium catalyzed cross couplings, which I end up doing a lot of because those are the ones where the mechanism is changing all the time, so it's perfectly amenable to high throughputs. But yeah, I think something that's really interesting is, yeah, when you're doing this array and just thinking about what I'm going to use ligands as an example because those tend to be a variable that you have many levels of when you're starting out with a new reaction, simply because, you know, they cause the greatest diversity in the results most of the time. And yeah, you will start off with the ligands that you expect to work really well. So maybe you want to pick 12 ligands, you'll pick 6 to 8 that you think are going to be good. So, you know, for a book called Heartwork, you might go for your T-butyl X-Fos, T-butyl Brett-Fos, things like that. Add Brett-Fos, explore the steric environment at phosphorus a little bit. Model-Fos, of course, we like Model-Fos. But then I found some really interesting results that I just didn't expect, even with having used those ligands multiple times in a high throughput manner. So I always remember once I did this palladium catalyzed deferrification, and DPVP was just an excellent ligand for that, and it just worked really well, and I hadn't really expected it in the context of that particular experiment. So when you get, you know, once you've picked out your ligands that you really expect to work, then for me that's time to move on to some, like, not silly ones, but definitely a bit more out of left field. High throughput is an opportunity to be doing that. I guess I'll show on the next slide how this works. We do our solid dispensing or liquid dispensing. Running the reaction, you need to think about heating, cooling. Stirring is actually something that you really need to consider for a 96 well plate. Hot plates can cut it. Analysis, preferably quantitative, and then reporting and closing the loop. What's important here, from my perspective, is making sure that this workflow is data driven and that we think about data at every step of the way. I like my Python script, even though, you know, it's written by me, not a real software developer, because when I design my plates, it gives me all the inputs and it gives me a template ready for the the analysis, the output of the LCMS to be put straight in there. And it kind of just guides me throughout the whole process. And that's probably the most important part of data management for the experiment that I'm running right now today. Yeah, I want it all to be guided. I do not ever want to be copying and pasting little bits of data between one place and another. I don't want to be typing things out typing numbers out unless I really have to. I want everything to be safe and reproducible and understandable by a computer later on. But yeah, I always thought, so I have a friend who works in, well, I always don't know how to describe his field, but he works in epidemiology, medical data, biomedical sciences. And he does a lot of big data work. And I remember saying to him that I always felt a bit like imposter syndrome about big data, whether I was a part of it or not. You know, I'm only doing 100 experiments at a time. That doesn't really sound like big data, which tends to be millions of data points. And he said, yes, as my friend Avi Roy, he said, I don't think about big data in terms of number of data points. Big data is high dimensionality, high volume data. And well, that's really interesting. I mean, that is what we have. Like, look at a single LCMS trace. So in our diode array, you know, this is kind of just relatively standard parameters, running at 20 hertz with a 1.2 nanometer resolution. So you're getting a big 3D graph like this, pretty complex, to be honest, for every single LCMS run you do in a 100 sample plate. Same with an evaporative light scattering detector. The MS results are really pretty big. You're going at 5 hertz for a range of MZ values, probably about 100 to 800 or 200 to 800. Positive and negative modes, add on as many other detectors as you like at this point. And that ends up being very much dependent on who manufactured your LCMS, but it ends up being perhaps 9.7 megabytes per chromatogram. That was an average of a couple of plates that I ran not too long ago. Or essentially a gigabyte per 96 sample plates. Can be a lot more, can be a lot less, depending on exactly what you're doing. So yeah, it does end up being big data essentially. And when I was talking about this with my biomedical friends, he was really surprised to know that actually our data are so complex in chemistry and in high throughput chemistry that we need to come in as humans and distill them down from this, like these big complex graphs. And we as experts need to come in and say to the computer, actually, this means that it's 57% yield in this particular reaction. We need to tell the computer what's important. I'm sure anyone who works in machine learning or that kind of thing, or in the IT and chemoinformatics side, probably know that more about this than I do in a way. But yeah, here's an example of a trace that I ran a couple of months ago for a decarboxylation, a proto-decarboxylation of a heterocycle. And in this case, I was trying to optimize for yield, and this is the best result. It wasn't a very big screen, but this was the best result from my screen. And actually this blue peak up here, that is my desired product, and this was the best yield. I'd asked what to optimize for. They said yield. I was like, great, okay, I'll do that. Here is your trace. And in this case, this actually was considered a success. We carried on with this particular method. It was a very, very challenging reaction. So we were actually happy with this, but probably you can imagine a lot of chemists would not be happy with a trace like this. And the thing is, when you talk to most chemists and you ask what they want out of the reaction, then they say, well, the highest yield, of course. And then you show them something like this and they're like, oh, well, I didn't want that highest yield. So it's quite difficult to understand what dependent variables people want. So here, the profile is really, really poor. And probably the chance of chromatographic purification may not be that high, at least on this analytical chromatographic method. I have a lot of very close running peaks to the desired product there. In fact, that contributes to the error bars on my understanding of the yield here too. So yeah, in many ways, this could be considered not great. Another thing that people often look at is the selectivity. So particularly in cases like radioselectivity, simply because that second isomer or more than second isomer could be really difficult to purify away, or it's more of a special case of a side product than something else. So many other things we could be optimizing for. Cost of reagents, scalability is definitely a big one. So I think that kind of there are ways to get around this. So like with scalability, it's something that I'm trying to do, is that, yes, I'll give the best result for right now, but then I found that quite often, in the case of agrochemistry particularly, sometimes you need to scale up really, really fast and you don't have any understanding a couple of weeks beforehand about exactly which projects you want to scale. And it's literally due to things like when plants grow, when crops are literally physically growing in particular areas of the world. You can't really wait for your crops. So it's kind of a little bit more agro specific, but there isn't always time to reconsider things fully when it comes to scaling up to kilo scale. So it could be useful at the point of me giving results to the chemists to say, not only this is the best result for now, but if you want to scale up, you might want to look at this alternative result, and point that out in the pie chart array. Maybe it has a nicer chemical and less toxicity, better user safety, operator safety, that sort of thing. But yes, it all comes down to, we always need the data, for two reasons really, not just for this experiment, but also for the next experiments we do, whether that's me following up next week, or whether that's in 5 years' time, somebody else doing something completely different where the same statistical model applies. So yeah, I think understandable by computer definitely requires some level of standardization. We don't like data dumps. We see a lot of data dumps. Just honestly, my biggest piece of advice is don't just dump your data into a massive folder on the LCMS. Please have some kind of metadata curation. Any kind of auto curation is always really good news as well, because we don't want to waste chemists' time, and chemists do not want to have their time wasted. So any kind of automatic curation is good news. And that's also something that I've tried to build into the Python script I built. So hopefully that will be passed on to more further reaching projects that work for everybody. Yeah, I guess I'd just like to kind of end with this. I think that, yes, the future is definitely automated. Automation seems to be getting bigger, and it's because of the data advantages. I think that's a really large part of it. So this is what we're doing. We do have a lot of custom middleware development. I mean, that is what I'm doing with my Python script. I'm part of the problem, but I'm hoping that at least the lessons we learn from that as a prototype, and if I make sure that I only consider it a prototype, can be passed on to bigger projects and to everybody else's advantage as well. I think a lot of what we do now is collaboration between humans and robots. I personally like that a lot. At the moment, in the future, then we might see more robots talking to each other, or middle robots passing things from one robot to the next. I know a lot of companies are working really hard on that already, and in some cases have those kind of things active in the labs. Reagent tracking can be difficult sometimes. Ideally, in an automation lab, particularly a high throughput lab, you want your reagents right there, particularly ready for the robot to use. That can also, in the future, be part of something that another robot can help with. So I don't even need to go and find my 16 ligands I'm putting into a high throughput screen. A robot can pick them out for me. It depends, you know, what the added value of that is, but being able to find them is enormous. It saves you so much time. We also tend to have immobile robots working inside fume hoods. Some people are working on mobile robots that can help with all aspects of what I've just been talking about, really. But this is largely where we want to be. Open source software is going to be a big thing. Trying to hack automation equipment can sometimes be difficult depending on the vendor. In many cases, you don't need to hack it. Sometimes you do. And the fact is, we want to have all the data from our experiments. We don't really want it in annoying proprietary formats, because who knows whether they're going to exist in 20, 30 years. We really don't. And also we need everything to be talking to each other, preferably with as much automation as possible. And if we can do that ourselves, sometimes that will save a lot of time if we can have everything talking to each other. Same deal with Internet of Things, which I know a lot of companies are working on now. For collecting data, I think Internet of Things can be huge. I don't want to personally be recording specific details of my temperature as it goes up and down on my hot plates. And I definitely don't want to be recording specific details of stirring environmental variables that probably don't matter, but then on the one time they do matter, or if I'm going back and trying to find out why my experiment just unexpectedly failed, I'd love to have all that data, and then I can see if something's gone wrong. So the less effort the chemist has to put in to collect those kind of things, the better, in my opinion. Of course, we're all moving towards AI, machine learning. I almost probably don't even need to say anything about that, because I think everyone else will definitely have their chance to talk about those kind of things. And self-optimizing reactions, of course, I work in reaction optimization. That's pretty much the holy grail, the ultimate of everything we do, so long as we still have that human input for our understanding. That will really help with all of these issues: data standardization, data management, everything like that. I should note it also helps when you're trying to convince people that this is a good thing. You know, you need data management because you want self-optimizing reactions, right? Anyway, yeah, I'd really just like to acknowledge my whole team at Syngenta. There's really a lot of people, I mean, potentially hundreds of people to acknowledge, but I'll thank my immediate team. So it's Chris Martin, Kenny Ling, Tomasz Michael, Claudio Batalocchio, and all the other great people I am working with, both at Gellets Hill and over in Switzerland. But yes, I'm very happy to take any questions if anybody has any.